We imagine the universe as a vast space dotted with a multitude of galaxies, which make up billions of stars, different in color and size. Trillions of different exoplanets orbit around these stars. We also know that there are enormous distances between star systems, between stars and exoplanets. What is between them? Is there an empty space or vacuum? There are small solid particles that are a fraction of a micron in size. Cosmic dust. It is often divided into interplanetary and interstellar, although obviously interstellar dust is not forbidden to enter interplanetary space either. Interplanetary dust, at least in the comparative vicinity of the Earth, is a fairly well-studied matter. Filling the entire space of the solar system and concentrated in the plane of its equator, it was produced mostly as a result of random collisions of asteroids and the destruction of comets that approached the Sun. The composition of the dust is essentially the same as that of meteorites falling to Earth. Due to such dust, it is possible to admire a pale cone of light over the horizon in good weather in the west, just after sunset, or in the east before sunrise. This is the so-called zodiacal sunlight scattered by small cosmic dust particles. However, interstellar dust is a whole other story. Its distinctive feature is the presence of a solid core and a shell. The core seems to consist mainly of carbon, silicon, and metals. The shell consists mainly of gaseous elements frozen on the surface of the core, namely hydrogen and oxygen crystallized in the deep freezing conditions of interstellar space, and this is about 10 Kelvin. However, there are also more complex molecular impurities. These are ammonia, methane, and even multi-atomic organic molecules that stick to the dust or form on its surface during its wanderings. Certainly, some of these substances fly away from the surface, for example, under the action of ultraviolet light, but this process is reversible. Some fly away, others freeze or synthesize. It must be said that the very notion of the cosmic vacuum as something completely empty has long remained only a poetic metaphor. In fact, the entire space of the universe, both between stars and between galaxies, is filled with matter, fluxes of elementary particles, radiation, and magnetic, electric, and gravitational fields. Roughly speaking, the only things that can be touched are gas, dust, and plasma. Gas is the most abundant in space, almost 99%, and then there's dust, which is almost 100 times less massive than gas. This matter is distributed in interstellar space very unevenly. Most of the interstellar gas and dust form a gas-dust layer near the symmetry plane of the galaxy disk. Its thickness in the Milky Way is several hundred light-years. Most of the gas and dust in its spiral arms and nucleus is concentrated mainly in giant molecular clouds ranging in size from 5 to 50 parsecs, 16 to 160 light-years, and weighing tens of thousands or even millions of solar masses. But even within these clouds, the matter is also distributed inhomogeneously. In the main volume of the cloud, the so-called coat, mostly made of molecular hydrogen, the density of particles is about 100 pieces per 1 cubic centimeter. In densifications inside the cloud it reaches tens of thousands of particles per 1 cubic centimeter, and in the cores of these densifications, millions of particles per 1 cubic centimeter. Stars, planets, and, ultimately, we ourselves owe our existence to this unevenness in the distribution of matter in the universe. Indeed, stars are born precisely in molecular clouds, which are dense and relatively cold. Interestingly, the higher the density of the cloud, the more diverse is its composition. In addition, according to the spectra, there are substances in interstellar space, the existence of which in Earth conditions is simply impossible. These are ions and radicals. Their chemical activity is so high that they immediately react on Earth. While in the rarefied cold space, they live long and quite freely. Finally, near the hot stars, gas exists in the form of ions. Powerful ultraviolet radiation heats and ionizes the gas, and it begins to glow. This is why regions with high concentrations of hot gas, with temperatures of about 10,000 K, look like luminous clouds. These are called luminous gas nebulae. Any nebula, in greater or lesser amounts, contains interstellar dust. Although nebulae are conventionally divided into dust and gas nebulae, they both contain dust. In either case, it is the dust that seems to help stars form in the interior of nebulae. Nebulae may be the most beautiful of all cosmic objects. However, dark nebulae appear simply as black blobs in the sky in the visible range. They are best observed against the background of the Milky Way. Whereas in other ranges of electromagnetic waves, such as infrared, they can be seen very well, and the pictures are very unusual. An interstellar nebula looks bright in two cases: either it is so hot that its gas itself glows, such nebulae are called emission nebulae. The other case is that the nebula itself is cold, but its dust scatters light from a nearby bright star. They are called reflection nebulae. Dark nebulae are also interstellar clusters of gas and dust. But unlike light gas nebulae, which are sometimes visible even with high-power binoculars or telescopes, such as the Orion Nebula, dark nebulae don't emit light but absorb it. When starlight passes through such nebulae, the dust can completely absorb it, converting it into infrared radiation invisible to the eye. This is why such nebulae look like starless gaps in the sky. Perhaps the most spectacular of these is the Horsehead Nebula. However, the dust particles may not completely absorb the light of stars, but only partially and selectively disperse it. The fact is that the size of interstellar dust particles is close to the wavelength of blue light, so it is more scattered and absorbed, while the red part of starlight reaches us better. So what is the role of dust in the formation of stars? And where, in fact, does it come from? In the total mass of cosmic matter, dust proper, for example, atoms of carbon, silicon, and some other elements combined into solid particles, is so small that it would seem that, at least as a building material for stars, they can be disregarded. However, in fact, their role is great. They cool the hot interstellar gas, turning it into that cold dense cloud, from which the stars then emerge. The fact is that the interstellar gas itself cannot cool down. To cool down properly, it needs a cooler, the role of which is performed by interstellar dust particles. Unlike heavier and slower dust particles, gas molecules fly fast. During high-speed collisions with dust particles, they lose speed and their kinetic energy is transferred to the dust particle. In the same way, it heats up and gives this excess heat to the surrounding space, including in the form of infrared radiation, while it cools down. Thus, taking on the heat of interstellar molecules, the dust acts as a kind of radiator, cooling the gas cloud. Its mass is relatively small, about 1% of the mass of the cloud's matter. But this is enough to remove the excess heat over millions of years. When the temperature of the cloud drops, so does the pressure. The cloud condenses and stars can be born from it. The remnants of the material from which the star was born are, in turn, the source material for the formation of the planets. Such material contains large amounts of dust particles. The reason is that, when a star is born, it heats up and disperses the surrounding gas, while the dust is left to fly around. After all, it is capable of cooling and is attracted to the new star much harder than individual gas molecules. Eventually, a dust cloud ends up next to the newborn star, with dust-saturated gas at its periphery. The Earth was largely made of interstellar dust particles. The metallic dust particles became part of the planet's core, which is why the Earth now has a huge iron core. If a galaxy is formed, then the source of the dust is basically clear. Its most significant sources are novae and supernovae, which lose some of their mass by dropping the shell into the surrounding space. In addition, dust is also born in the expanding atmosphere of red giants, from where it is literally swept away by the pressure of radiation. There are quite a few relatively complex molecules in their cool, by the standards of stars, atmosphere, about 2.5 to 3000 Kelvin. But here's a mystery that hasn't been solved until now. It has always been believed that dust is a product of the evolution of stars. In other words, stars must have been born, existed for some time, aged, and, say, produced dust in the last supernova explosion. Only what came first? The egg or the chicken? Was it the first dust, which was required for the birth of a star, or the first star, which for some reason was born without the help of dust, got old, exploded, forming the very first dust? If the Big Bang theory is to be believed, 14 billion years ago, when the Big Bang occurred, the universe had no other elements but hydrogen and helium. It was then that the first galaxies, huge clouds, began to emerge from them, and the first stars formed in them, which had a long way to go. Thermonuclear reactions in the cores of stars had to cook the more complex chemical elements, turning hydrogen and helium into carbon, nitrogen, oxygen, and so on. After that, the star had to throw it all into space by exploding or gradually dropping its shell. Then this mass had to cool down and finally turn into dust. Yet 2 billion years after the Big Bang, in the earliest galaxies, there was dust. Using telescopes, it was found in galaxies 12 billion light-years away from us. At the same time, 2 billion years is a too short period for the full life cycle of a star. At this time, most stars don't have time to grow old. It is a great mystery how the young galaxy got dust if there should be nothing but hydrogen and helium. It is highly probable that small interstellar dust particles, preserving in their shells a few organic molecules, including the simplest amino acids, brought to Earth the first seeds of life about 4 billion years ago. Obviously, it is nothing more than a beautiful hypothesis, though it is supported by the fact that the amino acid, glycine, was found in the composition of cold gas dust clouds. Maybe there are others, but so far the capabilities of telescopes are not enough to detect them.